Okay, welcome to the second part of the first Summer Academy lesson. I know that first one was long, had a lot of material. This one will not cover nearly as much material, but it would be a good opportunity for you to practice the skills that we worked on earlier. So today we're going to look more at rational functions. We'll graph a couple more, talk a little bit more about asymptotes and efficient methods of graphing rational functions. We'll discuss a little more about the sign chart, which is going to be a very, very helpful tool as we move on in calculus. And then we'll get some practice with other function types, looking at domain, range, x and y intercepts, and maybe even some average rate of change with some different function types that you've seen before, but may have not taken a look at in a little while. Now, if you don't see why this is the case, what I want you to do is go use your calculator and plug in larger and larger values of x to the point where you're using x values that are about as big as you can possibly think of. And notice how small the value is becoming. This is going to be a very important concept and is going to allow us to think about end behavior of rational functions in a very simplistic way. All right, so let's go ahead and get started. Here is another rational function, and our goal is to graph this rational function below. So using some of the tools that we have worked with previously, like looking at the domain, finding the roots, and then looking at the end behavior and drawing a sign chart, go ahead and give this a try, and then we'll work through it together. So starting off with the domain, and remembering that these are, we want to consider the values of x that we can plug in, that will give us a defined value of our function. What we realize is that with a rational function, we can plug in any x value so long as our denominator is not equal to 0. So to find out what values won't be in our domain, we need to set our denominator equal to 0. And if you tried to simplify this function straight off the bat, you probably don't even have to do a whole lot of work here. But when we set up this equation, there's a couple of routes, right? You can use the quadratic formula to solve for x, or you could factor out a 3. And then realize that this quadratic is actually factorable. You can find the two linear factors here. And so you end up with 3 times x minus 5 times x plus 2 equals 0. And so now you can see clearly that your denominator will be equal to 0 when x is either 5 or negative 2. So your domain are going to be all real numbers except, and I'm just going to put EX for except, positive 5 and negative 2. Okay. So remember that this means we can get as close as we want to an x value of 5, but we'll never actually be able to have an x value of 5. And so we can use that to help us construct our graph, and notice that the x value of 5 will never have a point associated with it. And so we have what's called a vertical asymptote, right? We'll get very, very close to that line, but we'll never quite touch it. And the same is true of negative 2. All right, now we need to find the roots, because once we find the roots, as I'm sure you've gathered from previous examples, once we have the roots, we know all the places that it will hit the x-axis. So we know that nowhere else on the graph will we intersect the x-axis, and that will allow us to create our sign chart and to figure out where on our graph our function is going to be either positive or negative. And that will get us about 90% of the way to having a very clear idea of what our function will look like. So the roots, of course, are where our function is equal to 0. So the x values that will make our function equivalent to 0. So we can set it equal to 0. And as we've talked about previously, any fraction is going to be equivalent to 0 when the numerator is 0 and the denominator is not. Okay? So we know the denominator will only be 0 when x is 5 or negative 2, so we'll keep that in mind. And now we realize is that, it doesn't even really matter what the denominator is. We just want to know when our numerator will be equal to 0. And so we end up having to solve when this quadratic will be equal to 0. And you can again use the quadratic formula. Or you can factor, and this will be x minus 2 and x minus 1. So we now know that our numerator, or in other words, our whole function, will be equal to 0 when x is equal to 2 and when x is equal to 1. And the good thing we just have to check is to make sure, and we've already noted this on our graph, so even if we tried to make a root at negative 2 or positive 5, we'd see that that's impossible because our denominator would also be 0. But we also can just check that none of the roots correspond to any of the values that would make the denominator 0, so both these roots will actually appear. So we can mark those on our graph. When x is equal to 2, we make that right there. And when x is equal to 1. And they're pretty close together. Okay. And so there we have two roots. And now we can move on to creating our sign chart and looking at the end behavior and the behavior that occurs close to the asymptotes. So now we have a pretty good idea of what our function is going to look like. And we can now write our sign chart to help us kind of determine where along our x-axis our function is either going to be positive or negative. Because since we know all the places where it intersects the x-axis, there's never going to be a place, for example, where it hits the x-axis to the left of negative 2. So we know that if it's positive at some point over here, it's always going to be positive at some point over here. And then we can just say, okay, well, what's going to happen as I go further to the left? What's going to happen as I go further towards my asymptote of negative 2? So we'll create our sign chart here. It's basically a recreation of the x-axis, if you want to think of it that way. And we'll mark on it all the what's called critical points. So those are the asymptotes and the roots. Because in between those points, we know that we'll either have everything be positive or everything be negative. So this is going to help us a great deal. Okay? So why don't you go ahead and fill out your sign chart, and then we will move on and look at the end behavior. All right, so looking to the left of negative 2, and all we need to do is plug in some value that's less than negative 2 into our function and see what we get. So you could try negative 3, for example. You could do this in your head, or you could plug it into a calculator. And you will see that to the left of negative 2, we are going to have a positive function. Okay? Let's go through the whole sign chart before we look at each section. So in between negative 2 and positive 1, in between here on this interval, we can either be positive or negative. And if you plug in some value, maybe 0, for example, 0 is easy because then we just end up with 2 over negative 30, which is a negative value. Be negative. And between 1 and 2, so maybe you plug in 1.5 and toss that into your calculator, and you'll find that you get a positive value. between 2 and 5, maybe pick a number like 3, and if you plug 3 into your function, you'll find that the value of your expression, of your rational function, is going to be negative. Past positive 5, and moving on towards positive infinity, so maybe using a value like 6, we find that our function is always going to be positive. And so now that we've done all this work ahead of time, kind of before we've actually sketched any of the graph, we now have a really clear idea of what our graph is going to look like. We know it's always going to be positive in this interval, negative in this interval, positive in this small interval here, negative in this interval, and then positive from 5 to positive infinity. And so what's left is for us to look at the end behavior, kind of go section by section, look at the end behavior, the behavior near the asymptotes on either side of them, and again, the end behavior towards the right. So let's start off and let's tackle the interval from negative infinity to negative 2. And let's start, of course, by looking at the end behavior as we approach negative infinity. And what I want you to do is just think about what's going to happen and maybe plug in some values to corroborate your hypothesis using x values that are getting closer and closer to negative infinity. Alright, so maybe you see it, maybe you don't, but if you're using a calculator, you should be getting values that are getting closer and closer to 0.33. And maybe you get, 0.34 or something, maybe 0.35, and so you're not quite sure what your function is going to be getting closer and closer to as x is getting further and further to the left. And there's actually a way that we can find this algebraically without doing this testing. And the way that we can do this is by combining a fairly simple idea with the idea that we kind of discussed in the opening question. Now, so the first thing to notice is that negative infinity is a very big number, right? It's very negative, but it's just in general, the absolute value of it is very big, right? And so what part of the numerator and what part of the denominator are going to be the biggest? Well, certainly the x squared term is going to dominate, right? When you get a really big number and you square it, it becomes so much bigger than just the number to begin with. And so you probably have a guess, just by looking, that these two terms are going to dominate. They are going to be the ones that determine what your value is getting closer and closer to. And so what we'd like for the rest of these terms, for it to be very clear that the rest of these terms do not matter, that they're going to just eventually be so insignificant that they're going to disappear. And the way to do that is to think about the expression that we looked at the beginning of the video, which was we had a number, 127. It was a fairly big number. But when we divide it by x and we look at x as x gets bigger and bigger to the point where it's approaching infinity, the 127 is totally worthless. That value is going to get closer and closer to 0 because infinity is so enormous. And so what we'd like to turn negative 3x and positive 2 and negative 9x and negative 30 into values that are actually going to become totally worthless. In other words, we'd like to turn negative 3x into something where we have just a number over x. And we'd like to have positive 2 turn into something where we just have positive 2 over x. And if you think about this, you'll notice that, look, we can do something to both the numerator and denominator so that each of these last two terms is going to be some number over x. Now notice we already have an x here, so just dividing by x won't leave us with some number over x. We're actually going to have to divide by x squared. And we're going to do this to both the numerator and the denominator. And when I say divide by x squared, we're actually going to multiply by 1 over x squared, which is obviously the same thing. And this is going to simplify, it might not seem like it, but this is really going to simplify our expression. So why don't you take a second and try and distribute out the 1 over x squared and see what you end up with. Okay, so what I did is I multiplied each of these terms by 1 over x squared. And so the first term would be x squared over x squared, and that's just 1. The next would be negative 3x over x squared. So x over x is 1, and then I'm left with just 1x in the denominator, and so I have negative 3x. 2 times 1 over x squared is just 2 over x squared. So I have 2 over x squared, and the denominator works out pretty much the same way. Now, think about this expression as x gets closer and closer to negative infinity. Well, does the x value affect 1 or 3? No. But it will affect each of these, and since x is in the denominator for each of these terms, as we get closer and closer to a negative infinity, this is going to become basically 0, as will this, this, and this. And so what we're left with is just that we're getting closer and closer to 1/3. And so our horizontal asymptote, what we are going to approach as we get closer to negative infinity, is going to be 1/3. Okay? And this is a strategy that you can use, and we will use in calculus a lot, to look at end behavior. Right? So we know as we move further and further to the left that we are going to approach 1/3, and we could mark this as 1/3. Okay? And there we go. And as we get closer and closer to negative 2, and here you can plug in some values that are very, very close to negative 2, you will notice that since it's positive, we're going to be getting very, very close to positive infinity. Right? And of course, the way that we can see that is, if you're plugging in something that's very close to negative 2, right, that was something that made your denominator equal to 0. And so as you get closer and closer to 0, well, when you're dividing by something that's very small, you're going to get a very big number. And since it's positive, it's going to be a big positive number. Yeah, that should be something that you're just getting used to. Okay. All right. Between negative 2 and positive 1, we know that our function is always negative. And since as we approach negative 2, since we know we're negative, and at negative 2 our denominator is 0, then as we get very close to it, it's going to be close to 0, and so our overall value is going to be very, very big, and it's going to be very big in a negative way. Okay? And of course we know that we have to then go ahead and actually intersect the x-axis at 1. Not a lot of work to do there. All right, in between 1 and 2, we know that we're positive, and hey, you know that you're going to intersect the x-axis at 2, so there's not a lot of work to be done here. You just know that you're going to be positive, and then you're going to come back down, and you're going to intersect the x-axis again at positive 2. Between 2 and 5, we know that our value of our function is negative, and since at 5 your denominator is 0, as you approach 5, you know that your denominator is going to get closer and closer to 0, and so your overall function is going to be very, very large, and a very, very large negative value. Okay. Similarly, on the other side of positive 5, we know our function is always positive, and again, by the same reasoning, we will be approaching infinity, but this time positive infinity, as we get closer and closer to positive 5 from the right side. And what you'll notice then, as we look at values getting closer and closer to positive infinity, going back to our expression that we've simplified here, each of these pieces that depends on x is going to get closer to 0. And so we're going to be left with 1/3, which means our horizontal asymptote, as we already found, is going to be 1/3. And we can make a couple of dashed lines there too. And there we have our function. Now, there's one thing that I want to point out that is very important, and that is that this horizontal asymptote basically saying that as we move towards negative or positive infinity, we're getting closer to 1/3. It doesn't have any bearing on the middle values of the function. What I mean by that is it's very possible that we reach a value of 1/3 somewhere in here. We might not, but there's no law, and there's nothing that that we've discovered that says that we can't hit 1/3. We know that we'll never actually get to 1/3 as we move further to the left, and we'll never actually get to 1/3 as we move further to the right, but that is dependent on x getting closer and closer to infinity. And so we want to be really careful that we don't mistakenly siphon ourselves off here in the middle of our graph. Okay, so a lot of things that we've worked on here, and hopefully you're feeling more and more confident with graphing rational functions. We're going to practice a couple more, and then we're going to take a look at some different functions that we've looked at before but not recently, and answer some different questions about them. All right, here's one more for you to practice with. I will definitely put a lot more in the assignment that I post on the Google Drive, but for now this is a good one to work with. One word of advice is that when you're finding your horizontal asymptote, you may see that you find something that looks a little different, and if you just take the time to sort of really think about what your function is doing, what the numerator and what the denominator are, it should make sense. So trust yourself and interpret the asymptote that you get in the way that you normally would, and you'll be just fine. The last thing is that I'm not going to post, and I'm going to post the solution, but I'm not going to show all the work that you might in coming up with your graph. And that's not because I wouldn't actually do that in real life. It's because what I want you to do is, if you have an error, I want you to say, okay, where might that error occur? Where did I mess up? And then go back into your work and pinpoint that exact place, so that you're starting to get used to analyzing errors on your own, because ultimately that's what you need to be good at, right? I'm not going to be sitting with you during the test in May and saying, oh hey buddy, by the way, check this, right? You need to be able to say, does my answer make sense based on the work? Is my work look correct? Okay, so keep that in mind, and I'll post the answer in about 5 or so seconds. Alright, so here you go. So here's where it looks a little different. Notice that what we want to do in order to evaluate our end behavior is that we want everything but the first two terms to just go away to 0. And so to get these two terms to go away to 0, we need to divide them by x. Alright, and what that will do is that'll leave us with 4x over 1. And as x approaches infinity, these are going to be totally meaningless, and what we're going to be left with is 4 times whatever x is over 1, which in other words is just 4x. And so what we're going to be getting very, very close to, although not quite, is we're going to be getting very, very close to y equals 4x. Okay, that's going to be essentially what we're looking at. We're never going to actually touch it as we move closer to infinity or negative infinity, but we're going to get very, very, very close to it. Okay, so that's one situation in which you're probably going to start noticing is there's kind of you can sort of, just by looking at your rational function, you're going to be able to tell what type of end behavior it's going to have, right? Is it going to be getting closer and closer to some sort of line that has a slope, for example here, 4x? Is it going to be getting closer to 0, or is it going to be getting closer and closer to some value like 1/3 like we saw previously? One thing to note here is we always put a curved bracket around infinity, because if you put a square bracket, that would mean that you could actually reach infinity, and that is kind of a contradictory statement in and of itself. Just imagine I asked you to count up to infinity, you would be here for infinity, right? So just one thing, you'll never see square brackets around on the side of an infinity in an interval, and if you do, you can go tell the person they're wrong.